As you see that in class, I didn't give some specific proofs of details of the proof of the conclusion or steps we gained in studying the heterogeneous and ensembles of the effect of noise in my project. So today's video is made for as a comprehension of the things I have finished in class. Now, first, still give you a brief introduction about heterogeneous ensemble and the effect of noise. So as you read this, this is the conclusion and about the brief introduction I gained in my own words. And the full passage is really like this for introducing the importance and what is the ensembles and the effect of noise. I studied heterogeneities and fluctuations are always present in microscope natural systems. All real populations of coupled dynamical elements are characterized by a certain degree of diversity, both in the individual properties of their components and in their interactions. And at the same time, they are subject to external forces orientating the environment. Those forces act as many different time scales and can be represented as randomly varying contributions to the dynamics of each single element. Disorder and noise are therefore important ingredients, and in any realistic model of a complex system, they compete with the mechanisms as introduce the emergence of order and thus drastically modify the properties of collective evolution. And with the two important conclusions we get is disorder and noise are therefore important ingredients in any realistic models of a complex system, as not from now. Well, the system we have learned so far are just some basic, simple linear systems with a specific equation supporting the output of the system. And the system we are going to introduce or we involved in this project are just those very complex systems with sometimes no specific details of input or output. And even they don't have a specific functions. But how this system works, and you see in modern civilization, those systems always converting a massive input into a regular output, which means they can't find a balance between disorder and order and find the order in disorder. So what support them to do that? That is the heterogeneous ensembles and the effect of noise. This theory helps this system, those complex systems, find order for us in this disorder input. And secondly, they compete with the mechanisms that introduce the emergence of order and thus can dramatically modify the properties of collective evolution. These two are the most important conclusion in the brief introduction of heterogeneous ensembles and the effect of noise. I come next slide. Still, there are 5 topics we are going to tell. The first 4 are just some details of the proofs of steps we gain in this series. And the last number 5 is a summary of the conclusion of the whole series. So start from the first one, transition to frequency synchronization. To begin with, give you a brief idea what this is. It began with the heterogeneous system by analyzing the emergence of collective evolution. And after this evolution and analyzing, it becomes a phenomenon. And what we call this phenomenon can be analytically studied for a large examples of globally coupled phase oscillators whose individual evolution is given by this function. Here, phi prime I is the individual evolution of each independent or dependent phasor oscillators. And between these steps and these steps, there is still another equation where omega I prime is called the effective frequency, and where effective frequency is gained in a time long enough that we can consider this system as a non-periodic system. So the effective frequency omega I prime is defined as this one. So in general, the frequency omega phi I dot of each oscillator differs from its natural frequency. The natural frequency is this one. And so between these two variables, here we find the effective frequency. So a cluster formed by a fraction of oscillators with identical effective frequencies appears as some critical value of the computing stress. And for if we pick I and J in a cluster of systems, such that we pick the I system and the J systems, and it gives us omega I and omega J separately. And in this cluster, we have omega I prime equals to omega J prime equals to, here we define omega I as the synchrotization frequency. It's right like this, just the thing we are talking about. This is the definition of omega. And these phases of these oscillators are not identical. The number of elements inside the cluster increases as K grows beyond the critical coupling Kc. Just in this system, not to mention further because it will be a long story, there is something called a critical coupling, and we will define as Kc. This is Kc. When K is larger than this Kc, what will happen is that the elements inside the cluster increases as it goes beyond. And if the K is still here, this is number, it will not increase, but as long as K is bigger than Kc, it will increase really, really fast. So back to the main topic. The important conclusion of this transition frequency synchronization is that we get this function. So how does this come this function? As we introduce omega I prime and this omega, this O, we gave a statistical description of the solutions in this equation. The solutions in this equation here can be generalized as an integral written like this one. Forget about the mathematical steps we are using here. You just need to mention the conclusion. Is how we define from a summary to an integral of this solution. This is a detail of the solution, and the evolution equation for phi I takes the form of this one, omega t and exp. Defined as this one. And back to the slides. So where Kc is just what we mentioned, is the critical coupling Kc. Once K is bigger than the critical coupling Kc, and the elements number is increasing really, really fast. So it's defined as this one. And here, tau xi an order parameter for the synchronization of this transition. It will appear very frequently in the following slides, and just remember it is an order parameter for this transition. So this is the steps we are going to deal with in the following. Effective frequency I have mentioned before on the blank page, and relation between phase and the natural frequency omega. Here is omega of each oscillator yields a all new equation written here as this one, applying the definition of tau t. And you can still find that if we assume the existence of additional solutions where tau is not equal to 0, separate real and imaginary parts and get two couple equations for tau and omega as functions as g omega and capital K. So we get these two equations. after getting these two equations, the first thing is we need to assume that if the distribution of G omega is symmetric around the frequency omega 0, and if it is symmetric, then we can say that G omega 0 plus omega equals to G omega 0 minus omega. It's just something like this one, symmetric. And this is the central line around which is symmetric. Then there is about a certain critical coupling intensity, Kc. Here Kc comes again. So just need to prove Kc exists. So in other words, a sinuous constant move with a collective frequency omega, capital omega equals omega 0 appear as Kc. So we just need to draw a very simple diagram of tau and k, where if we define as 5, and here we define as 1.0. So it might look like this. And once it is over the critical point, it is like this one, or like this one. And not to mention, it's just an example, upon which we have the second order around if tau is equal to 0. So after this equation, we get this one. And there's no actual mathematical meaning of this one. It's just a middle step of the final conclusion we want to get. But you see that, note that this one, G prime prime omega 0, is always is always smaller than 0, because since G omega reaches a maximum as omega 0, so the polynomial equation has non-zero rules when k is bigger than kc. And so what's the solution then becomes? By applying this equation and the following solution we gain from above, kc becomes this one, and tau becomes this one. So this is the solution. And to push this statement further, we know for probably to a symmetric distribution of natural frequencies. This is natural frequencies, read like this. G omega prime is the distribution function of natural frequencies. So for a symmetric distribution of natural frequencies, then G omega prime can be written in this way. But so for namely, if we use work with Lawtonized distribution of natural frequencies. So suppose that we study below another case where explicit results can be obtained, namely in this way: G omega equals to 2 alpha 1 plus alpha 1 minus omega 0 power alpha. Then for omega minus omega naught absolute value, if it is smaller than 1 and plus this condition, G omega is equal to 0. So otherwise, here alpha is greater than 0, since G omega is symmetric around, as you see, G omega is symmetric among omega 0. So limiting the analysis to a region where these two multiply together is less than 1, we limited the region we are going to study into this one. So which includes a particular entertainment transition. So we found the solution to the function becomes like equals to a very complex solution. And here just see some mathematical proof and mathematical theory, just forgot about it because what we are focusing on is the conclusion we got in the final step, that is step 5. What we got is this one. So with Kc equals to pi 1 plus alpha and 4 alpha. So consequently, near the entertainment transition, the order parameter behaves like our tau is positive to k minus kc power 1 over alpha. So this critical exponent 1 over alpha is in general different from that form formed in what we previously got in that equation from another definition of tau. And in this case of a Lorentzian distribution of natural frequencies, this exponent is determined by the shape of g omega at its maximum and equals to 1 over 2 only for quadratic profiles. So that is all the steps and all the conclusions we need in step 1. And the following is the frequency clustering. So as you may not have any specific idea about what this is, so let's give you a brief introduction. This theory of frequency synchronization is assuming that as element becomes entertained and move at the same frequency, only the cluster of synchronized oscillators is presented in the ensemble, and otherwise they remain silent. This is the case when the distribution of natural frequencies g omega has a single maximum. So what we mentioned before is that this depends on the shape of g omega at its maximum. Here we use that again. Depends on the maximum and how many maximum or how many peaks does g omega has. So when g omega has more than one maximum, if we enjoy like this, more than one maximum, just something like this. And what will happen is that it may happen that several clusters appear during the synchronization process. For the study of frequency distributions with a single maximum, just a different case. Case one is this one, and the case this one. A single maximum and nothing else left. Then the number of oscillators, if the number is large enough to trigger mutual synchronization, we find that once formed, these clusters behave as interacting individual oscillators, and with each of them affecting the motion of others. And so that's how we can generalize the idea that today's most of the system can find order in disorder. Now we are just begin. Then how to quantities of tau t. First give you a brief diagram of tau bar and capital K. What does it look like? And then the gradual emergence of coherent evolution as coupling becomes stronger. So we take time average. So this is the definition of tau bar and also in a long period signal. When K increases, tau bar grows steadily, and the variation of tau bar is faster in zones where the collapse of a large cluster takes place. What is still mentioned is that the action of a cluster on the non-entertained oscillators and on the other clusters is quantitatively equivalent to an external periodic force with the frequency of that cluster. That is the interesting part is, as the t goes to infinity, long period interval, we assume that it is no longer periodic, but it is back to periodic again. Moreover, when most of the ensemble is entertained in a few clusters dominate the collective dynamics of the system, non-linearities in the interaction function induce resonance effect at frequencies and do not collide with those clusters. Well, we'll give you a brief example. Suppose that at k at almost 0.06, and numerical results show that along the whole interval of coupling in densities when these lateral clusters exist, and we define their frequencies are omega c prime equals to 2 omega a prime minus omega b prime, and another is omega 3 prime equals to 2 omega b prime minus omega a prime, and omega a prime, omega b prime are the frequencies of the central clusters. So this is the conclusion we get. For the original example is those can result in the information of the frequency synchronized as the clusters at higher harmonic frequencies. And if we define k equals to 0.07, the difference between these two are at 0.07, apart from some non-entertained elements, the ensemble is divided into 4 clusters. So clearly, 2 large clusters with the central frequencies result from successive aggregation of small groups, and the other 2 on the other side appears rather subtly. And so in this 0.7, there are 2 that's very specific, and this is the main point. And there are 2 left in k equals to 0.07 as the same as k equals to 0.06. So back to the slides. This is the conclusion we get from there. And the third is the fluctuating forces. Fluctuating forces give you a brief introduction that in many potential applications of the ensemble of the interacting oscillators, the time needed for a signal carrying information about the internal state of a given element to reach another element may be the same order or larger than the typical time scales of the individual dynamics. So in such cases, the assumption that each element acts instantaneously on another element of the ensemble implicitly does not hold. So this means the system gets more complex. So on the other hand, they might hold, or on the other hand, they might not hold. So there are complex reasons in that. So the system makes the system not that simple. So the role of this kind of delay in the collective behavior of the interacting elements has been emphasized, particularly for biological systems. And therefore, it is a little bit interesting and meaningful to analyze the dynamic of coupled elements, and time delays are introduced in the interaction functions. So in this case, we define it is still the original phi it, but it is enhanced into the following equation. We just make some comprehension and supplement materials into the equation we gained. And here I equals 1, 2, point, capital N. So the effect of random functions on interaction models have been found that noise stabilizes the stationary solution given as this function. But still, there is need to show that to gain insight on the effect of time delays in the collective dynamics of coupled phasor oscillators. Still, we consider element this 1t dot and element 2t dot. And during the following slide, during the previous slide, we write like this one: omega 1 plus k over 2 sine phi 2 t minus tau minus phi 1 t. And written as above, this is omega 2 plus 2 blah blah blah, and here change to phi 1, and here change to phi 2. So this is phi 2 while this is 1. This is phi 1 while this is 2. So the others remain unchanged. So this equation have the solution in the form like this one: 1, 2, no. 1, 2, this is phi, 1, 2, t, omega t plus or minus alpha over 2. So these equations can use the properties of this equation. That is, we gain new equation. And omega 1 plus omega 2 equals to 2 omega plus k sine omega tau cosine alpha. And so this equation gives the neutralization frequency and then the phase difference as functions of a natural frequency is defined as follows. So still, you don't need to know the mathematical meaning of this function. You just know this is one of the most important steps in proving this theory. And so when omega, what will happen when omega is known? Then if omega is known, the phase difference is calculated at this one. When omega is known, then we can directly calculate alpha equals to arc sine k cosine omega t omega 1 minus omega 2. So even in the case of identical numerator frequencies, such as omega 1 equals to omega 2 equals to omega, then the equation reduces to a more simpler form. So we just need to pull that omega out, which becomes omega equals to omega minus k over 2 multiplied by sine omega t. Then this is the conclusion we got here. And to get this, for in case 1, the parameter regions of the Fokker-Planck equation. So what is the Fokker-Planck equation? A Fokker-Planck equation is a mathematical method we used here, which yields the stationary solution is unstable in this occasion. So when the stationary solution is unstable for I is equal to 0, then increasing the level of noise induces a transition and it becomes stable. That's why it can find order from disorder in our real world. So let us see case 2. Then if this is fully synergized of cluster states are tables for S equal to 0, then the transition takes place at finite noise intensity at capital S. And the finite time independent order parameter tau bar can be defined as the temporal average, and the average is defined as this. Nothing new, but it improves some facility and equipment. During a long time interval, still this goes to infinity, near the critical point when the stationary distribution becomes stable. These order parameters and behave like this one. Then the above interaction model holds. And the fourth one is time-delayed interaction. So time-delayed interaction, how to give you a brief introduction about this. So what is time delayed? It's obvious it's delay of time didn't arrive in time. That is time delayed. So in time delayed interactions, in populations, interacting organisms, communication involves virtual acoustic or chemical signals that takes a long time to travel through physical diagrams such as air, water, or soil. Then the assumption that each element acts instantaneously on another element of the ensemble does not hold. That's why I have mentioned that this does not hold in previous like this one. Then dynamic of the coupled elements when time delay is introduced in the interaction function works like this. time delays can be introduced as the following model, global coefficient oscillators. This is still nothing much changed from here, what I put up here. Also still, when the delay, if we can consider tau ij is greater than 0, then this represents the time needed for the signal carrying information about the state of oscillators from I to j. So this is the time. Then what we get from the previous four, first we get this solution, and second we get this one. These are two important results in 1.1, and then in 1.2 what we gain is in a long period of signal taking time average, shows like this, and as k increases, here we draw a diagram, tau bar goes steadily. That is what the conclusion we need to memorize. And then in fluctuating forces, still we need to remember this conclusion, and the steps it is being created or it is being concluded, this equation. And noticeably that if once I equals to 0, this stationary solution becomes unstable. Then can I say if it fully synchronizes, and we believe at this one and this one, those equations are of great importance in the following slides. And in the time delayed interactions, the coupled phasor oscillators are being defined this way. So here's the basic steps to obtain the self-consistent value for tau and phi, which is, then we first need to assume that the interactions when ki and noise satellites are assigned over ensemble following prescribed by distribution. Then we have this triple integration here. Now for the further reduce of the equation tau, because we know that tau is complex, then we reduce this one. So here we get tau equals to I1 multiply this one. And if we further reduce the equation that of the derivatives of the partial interactions, it reveals that those two people are still alive. Then from above, we can conclude that there are obviously two extreme situations. The first one is the coupling strength and the noise intensity of each oscillator are fully uncorrelated attributes. Then distribution can be factorized because they are supposed, here we define those peoples as elements in a complex system, and when the elements are not interacting with each other, they can be calculated linearly and separated. Then critical noise intensity equals to becomes this one. Now the conclusion one we find in the condition one is that in an ensemble with heterogeneous coupling, noise is able to surpass the signalization as long as the function is integrable over 0 infinity open interval. And then the opposite extreme to case 1 is examine the case where the distribution between coupling strength and noise intensity is so strong that two attributes is given by function of the other, this one. Whereas is defined to be the function of k, and omega is defined to be omega 1k multiplied by tau s minus this symbol can multiply k. And the conclusion 2 we found in this is that the correlation between the coupling strength and the noise intensity of each oscillator becomes a dramatic relation between k and s. So this shows as R grows positive. On the other hand, oscillators with large coupling strength suffers. On the average, large noise intensities and synchronization may be inhibited by noise. and this is the relationship. This is the 100% completed relationships between K and S. No special occasion or no special arrangement. It's just this function which satisfies for all who wants to behave like a couple oscillators. Then still, at the end of lecture, give you a very detailed impression. In figure 1, that order parameter in tau is spotted as a function of a noise parameter for several values of exponent q. And there is a typo which here behind here as there is a figure 2 displays the incremental order parameters as function of s. Then you see the difference is that I want to mention one thing is that below here are all the region of this diagram. That doesn't mean they are lines. Just if we like Q have a smaller intersection, we can gain these under beneath this are all of our study area, and those Bell diagrams are close with parameters are capital S. So, as a summary, we give you a final conclusion. Consider that a heterogeneous ensemble of a coupled phasor diagram is subject to external functions. And in this function, the coupling stress and the effect of noise can be different from each oscillators, which corresponding to we pick a cluster of oscillators and namely them Ij and Ik. Then with homogeneous coupling synchronization behavior, we can find that the effect of noise can be different for such oscillators. When we use those very simple tool to test whether the system's property, we are actually using this theory. So, but sufficiently large homogeneous fluctuations inhibited synchronization. We have shown here that on the suffer hand, synchrogeneous noise may not be able to inhibit it. Then a similar complementary effect takes place with very small response to noise can raise surprise. As we have gained experience and we have some experience in reality that the magnitude of number when in these two occasions, although the other parameters and the variables and functions are the same, only this change, and then they become indifferent. They become no longer indifferent. They have the different personalities. A similar complementary effect takes place when noise interstates are in turn heterogeneous over the ensemble and axis of oscillators with very small slopes to noise and supra-synchronized behavior. And in this more genetic situation where the complex stress and the noise intensity of each oscillator are correlated, the two attributes may control each other. The large complex which favor synchronization compete with large fluctuations, and this intends to inhibit the coherent behavior, where this precise form of their correlation define whether the dynamic homogenization transit exists or not. So that is the end of our project. So as a summary, although I chose a very big project which cannot be finished something like in 10 minutes or 15 minutes, but actually we gain the new knowledge of the basic idea how to find order from disorder. That is, we depends on this heterogeneous and the effect of noise. We are actually using this equation every day and at every time. But since it is related to signal and system, I just want to let you know that signal and system are just something more than calculation and some programming. It can be an idea that is generating most of the orders of this system. So So that's all about my project. Thank you for listening.